Bernoulli's theorem. You see, contribution of Bernoulli is in hydrodynamics and also in gases. Bernoulli is known as father of kinetic theory. Here, Bernoulli's theorem has two conditions. So, before we start, let's point out those two conditions. It's applicable to ideal fluid only. So, this is the first and foremost condition. And second is the flow should be streamlined. So, to begin with Bernoulli's theorem, let's start from here only. For an ideal fluid in streamlined flow per unit volume, this is one additional. You might say you have bracketed the whole thing, means it is going to be applied for unit volume only. So, three terms you need to remember. One, for ideal fluid in a streamlined flow per unit volume, the sum of three energies is constant. What are those three energies? Kinetic energy, potential energy, and the pressure energy. Once you say per unit volume and then you use all the three terms, that way you have reduced the whole size of Bernoulli's theorem. Now it becomes easier to interpret that for an ideal fluid in a streamlined flow per unit volume, the sum of kinetic potential and pressure energy remains constant throughout. You see, if you take the term kinetic energy and you want this whole thing for unit volume divided by volume, you'll get this half dV square. So, this becomes kinetic energy per unit volume. To be more precise, you could use the term kinetic energy density, because divided by volume is another name of density, mass upon volume density. So, this is kinetic energy density. Likewise, you have the potential energy HdG. Oh, sorry, this is pressure. You have the potential energy mgh. You divide it by volume, it becomes density dgh. This is the potential energy per unit volume. Similarly, you will get the term pressure energy is P delta V and pressure energy per unit volume is going to be P only. If you sum up all the three terms, this theorem says that the sum of these energy, these terms per unit volume, always remains constant. But the very important condition is this is applicable for streamlined flow and ideal fluid. If the fluid is ideal, it simply means it is incompressible. It is non-viscous. No fluid could be ideal. Remember, either liquids are viscous but incompressible. 50% of the criteria is okay with liquids. Gases are highly compressible but very low viscous. So, there also you can't say that gases are completely ideal in nature or even the liquids. None of the liquid or gases in the nature are ideal. But still, it's purely hypothetical. Same hypothecation here is, as we consider a smooth surface frictionless, that's also not impossible, that not possible. So, here this theorem is applicable only for ideal fluid streamline flow, and that's what is written here exactly. The condition is also imposed over here. Suppose the flow is horizontal. Liquid that we have considered is not getting changed. D will remain same, G remains constant. If apply the criteria that it is a horizontal flow, H will also be constant. Then in that case, only two terms are left, P plus half dV square. You see, this is also known as this short form of Bernoulli's theorem. This is known as Hawksby's law, but that's not so popular. This law says When pressure will increase, velocity will decrease. Velocity will increase, pressure will decrease. This you have to remember, and you'll see so many examples. When the velocity increases, the pressure decreases. For example, when two trucks are passing side by side, if the velocity becomes greater, pressure automatically will be less between them. So this is maintained throughout. One very important thing is also there, that if you divide the whole equation, this equation, by dg, you are going to get another format of the whole thing. This is, now you get three terms. Again, these are known as heads. You could say for ideal flow, ideal fluid in streamline flow, sum of three heads is constant. What are those three heads? This would be known as pressure head. This is velocity head, and this will be known as position, or you might say gravitational head. So, as far as Bernoulli's theorem is concerned, this is another form of conservation of energy. We talk in terms of energy because these terms represent energy per unit volume. This is pressure energy per unit volume, kinetic energy per unit volume, and this is potential energy per unit volume. So, we define in terms of energy per unit volume, here in terms of head, and you have to remember that P is pressure, never forget. So, in Bernoulli's theorem, you start with pressure. Obviously, pressure could be added with pressure only. So, all the three terms are also standing for pressure. This will be known as static pressure. This will be known as static pressure, and this half dV square is also sometimes known as dynamic pressure. So, this theorem could also be interpreted by this method, that sum of two pressure, this is dynamic pressure, this one, and this is static pressure. Sum of static and dynamic pressure remains constant throughout for ideal fluid in streamline flow. This is another version. So, overall, I have told you four versions of Bernoulli's theorem. You could use any of the version depending on your choice. As and when required, you could use any form.